Okay, good morning. Let me start with the main argument of this subsection. So if you recall, what are we trying to do? We are trying to get optimal bounds for the Stieltjes transform of this of the empirical eigenvalue density. So we spent some time proving a local law where we proved that this parameter lambda, which is by definition which controls the entries dij minus m. We proved that this is small, but this bound is far from optimal. You saw it already in the proof. We made lots of estimates which were not particularly sharp. And now we're aiming at optimal bounds, and there are various applications of that. The one we will see is the so-called eigenvalue rigidity phenomenon. And it's important to understand the distribution of the largest or the smallest eigenvalues, for example. And this in particular implies immediately that this quantity that we call theta, which was just g minus n, was bounded by the same thing. And this is far from optimal. And so now we would like to derive optimal bounds. We saw last time that getting these optimal bounds is a somewhat subtle affair. It involves an averaging mechanism between random variables which are correlated. So you have an averaging of random variables which are not independent. They are not completely correlated, but they are not completely independent either. So there's something somewhat delicate going on. And we will do this using this method of cumulant expansion. So the strategy. So last time we saw the cumulant expansion. Now you've worked on the problem set, so you know everything about cumulants. They are very nice and powerful algebraic objects. And the strategy in this case is to derive an estimate the same as before. So derive an estimate well, we want to estimate this guy, right? We want to estimate g minus n. And we saw already in our previous proof of the weak local law how to do that. And that is, you show that G satisfies a quadratic equation which is very close to the exact quadratic equation satisfied by M. And then you have to do a stability analysis of the roots. So the quadratic, now let me introduce a notation. This capital P is the polynomial of degree 2, always the same one. So I plug in the argument g, so this is always the same second degree polynomial. So we will estimate this object. We wish to show that this thing is small. If we can show that this thing is small using a bootstrapping argument, we will be able to conclude that g is close to m. And how does one do that? So how do we use the cumulant expansion? If you recall, the cumulant expansion involved something of this kind. So it allows you to compute something of this type here. The crucial thing is there is an expectation, right? It can only be applied within an expectation. So if we want to estimate such an object, we have to put it somehow inside an expectation. If we just take the expectation of this guy, no matter what we can, no matter how precise bounds we obtain on the expectation of this, it will not allow us to say anything about this object as a random variable. So in order to estimate this guy, we will apply a high moment approach using Chebyshev's inequality. So we will take a high moment of this object and estimate that. And then by Chebyshev, if you know that the high moments are estimated, you know that the object itself is estimated with very high probability. So we will estimate this object. So we will take P of G, and we take it to a very high moment. Now, algebraically, so this is of course a complex number. So we want to estimate this guy to the absolute value of this to some high power. And you know that absolute values are much easier to deal with if the power is even. So let me call this power 2p. And for some large but fixed So fixed means it does not, so if you recall we have this convention of fixed or constant, which is something that cannot depend on n. So this p will not depend on n. So we will generate lots of constants which behave quite badly potentially as p grows, but we don't care about that. P is always going to be some fixed number. And Chebyshev. And Chebyshev's inequality. Does everyone know Chebyshev's inequality? Yes, I guess. Has anyone not seen Chebyshev's inequality? No, everyone knows it. It's the most basic inequality in probability. And now, so the argument I'm about to give you is I think it's a very nice argument. It's a very powerful argument, and it's a prototype, maybe the simplest prototype of a wide variety of arguments used in the study of random matrices. I would like to make it as transparent and straightforward as possible to avoid, these arguments can get somewhat technical, so I would like to make a few simplifying assumptions. The first one is kind of obvious if you think about the cumulant expansion we saw last time. H was a real random variable. I will apply it to my complex matrix, my matrix entries, which in general are complex, so there's a discrepancy. So I would like to assume my matrix entries are real. So we can literally apply the formula we saw last time. So suppose that Hij is real for all ij. This is not a big assumption. I will not discuss it here. I think it's not such an interesting thing, but if you are interested, you can work it out yourself. There is a direct analog of this cumulant expansion for complex random variables. The proof is the same. It's not hard. You just have to figure out on the right hand side you will have holomorphic and anti-holomorphic derivatives, but it works exactly in the same way. So it's not really a more complicated thing. The notation is a bit easier in the real case, so we'll stick to that. And there's another assumption. If you recall, I told you, and we saw in the proof of this result here, that the precise variance of the diagonal entries does not matter. Our assumption on the diagonal entries of H, if you go all the way back to the definition of a Wigner matrix, was that the expectation of Hij squared. So it's important that the off-diagonal ones are exactly equal to 1 over n. The diagonal ones, it doesn't really matter. So I had this big O of delta ij, which means that if I is equal to j, then this can be any constant. It can depend on I and j. It just has to be bounded in n. And here I would like to fix this number to be precisely 1 plus delta ij. So the variance of the off-diagonal entries is twice the diagonal entries is twice the variance of the off-diagonal entries. Again, this is not an important assumption. If I did not make this assumption, I would just get a few extra error terms in my proof, which are very easy to estimate, but they somehow obscure the argument. So I would rather not deal with them. If you are interested in this, it's an easy exercise. You can work out what happens if this is not satisfied. You can follow the steps we will do. At some point you will see, aha, we get some extra terms, but then you will also see, well, in fact, these terms are easy to estimate. Okay, so these, a remark, by the way, that these are precisely satisfied by GOE. So the standard Gaussian orthogonal ensemble has this covariance structure. Okay, so before we begin the argument, one further observation which is important. So we will apply this. I should have written out the formula in full. Let me write it here. So if you recall, it says Okay. So I have to differentiate, right? So and then I have the remainder term. I think I wrote it up in this form using this notation. Let me just check. Yes, I used this notation. Okay. So recall this was the formula we are going to use. Now, this means in particular we have to differentiate some function, k times, with respect to h. Now, h in these applications you will see is going to be one of the matrix entries. Now, there's a slight nuisance caused by the fact that the matrix does not have completely independent entries. It's symmetric, which means that these entries, if I take my matrix here, if I have an entry here, this entry and that entry are the same. So if I differentiate in one of the independent random variables, I will simultaneously change both of these entries, right? So I have to do this differentiation carefully, and I do that as follows. So I define a basis. I will define a basis or a generating set, at least, of my space of Hermitian matrices, which is going to be, so I will write down a formula which looks terribly complicated, but this is a trivial fact. So it is a canonical basis. It has so if I is not equal to j, it has two ones. Otherwise, it's a matrix that has two ones at the position ij and ji, and everything else is 0. And if I is equal to j, so this is the case I not equal to j, and if I is equal to j, it has just one. It has a single one at the position ii. Okay, is this clear? This is basically the definition. I'll write down a precise formula, but this is my object. So this is my matrix Eij, and so it's defined by, so it's a matrix, k and l go from 1 to n, where Eij kl, so the kl entry of this matrix is equal to, well, I have, let me first consider the off-diagonal case. So I have the case where k is equal to I and l is equal to j. So ik delta jl. And then I have the other one where k is equal to j and l is equal to I. Okay. So this is this. So this is the correct expression for the off-diagonal matrix. Now for the diagonal one where I is equal to j, I see I get exactly this, but I get it twice. So I have to divide by 2 in the diagonal case. So this is my matrix. So this is, if you like, precise expressions. It looks kind of unreadable, but it's just a trivial definition of this basis. And now I define, so when I differentiate with respect to hij, when I vary, you see, if I vary hij, then what I'm varying in the matrix is actually hij times this matrix, right? If I change hij a bit, then I will vary my matrix in the direction of this matrix Eij. So I will define the partial derivative . I will define the partial derivative, which I denote by partial ij of some function f of h, as being the directional derivative in the direction Eij. So this is equal to d over, let me write it like this, dt, at t is equal to 0, f h plus T. Okay, so I'm differentiating in the space. You see, I want to remain always within the subspace of symmetric matrices. If I just differentiated one entry, this guy here, then I would be differentiating in a direction that is not within this subspace of symmetric matrices. So now I'm differentiating in a direction, Eij, that lies in the space of symmetric real matrices. Okay, then, and this is a little calculation which is crucial that we will need throughout the proof. You see, it's kind of obvious we will need this. We will, if we apply the cumulant formula, we haven't quite seen yet how this H will pop up, but that's going to be easy to see. We will have to differentiate objects of this kind. So polynomials of G, of little g, which means just expressing little g as an average of big G's, we will have to be able to differentiate entries of big G. And there is a simple formula for this. Remember, in the very first problem set, you worked out some basic facts about resolvents and so on. And let me assume I is not equal to j. I'm differentiating in this direction. You should always work these things out in the two different cases. I is not equal to j and I is equal to j. If I is not equal to j, then this amounts to differentiating in this index and differentiating in that index. And if I differentiate in this one, in ij, I get minus, so let me put a minus here, minus gai gjb. And if I differentiate in that direction, then I get gaj gib. That's if I is not equal to j. If I is equal to j, then these two terms are the same, and I only get one of them, which means I can compensate by dividing by 2. So I can write the whole thing like that. So this is a formula that is correct for all I and j. Okay, so to derive these kinds of formulas, you just consider the two cases when I is not equal to j and when I is equal to j separately. And then there's this nice way of writing them both in the same formula by adding these kinds of factors. Okay, so that's the preparation. So let's start the computation. So how does one start? We have to use, of course, we have to use some defining characteristic of G in order to I mean, we have to use the fact that G is not any old matrix. It's the green function of H, and we start instead of using. So the algebra behind this is much more trivial than using the other method. We don't use any Shor complement formulas or resolvent identities. We just use these kinds of trivial resolvent identities which come from the resolvent expansion. And the only fact we use about G is that it's the inverse of H minus Z. So let's write, if you recall, I mean, this is by definition, H minus Z times G is equal to the identity. That's by definition. So if I can rewrite this, and I take now a diagonal entry, so the entry II of this guy. The identity II is just 1. ZGII is, well, ZGII. And this is equal to HGII. Now I can average over I. 1 plus ZG is equal to, and let me write this as a 1 over n, sum over I, j, h, I, j, g, j, I. Okay, this is what I get if I average over I on the right-hand side. And now you see this is how I will get something that resembles this guy here. I have an h, which is going to be this h here, and then this h is going to be multiplied by some very complicated function, which is going to be a product of these green function entries. But it's a function that's smooth. In fact, it's analytic, so we can differentiate it as many times as we wish, and that's what we will do. So this whole argument relies on an algebra which is in principle completely straightforward. It is the algebra of what happens when you differentiate green function entries or polynomials of green function entries with respect to hij. And the differentiation of these entries is very straightforward. It's just using this formula. So the whole argument is just really going to be an application of this formula in an organized and controlled fashion. There are some estimates to be done along the way, but they are relatively basic. There's basically two observations you have to make in order to do the estimates, and we will see them. So let's start. So I have this function. I have this polynomial p of g, and since I will keep on writing it a lot, I will just abbreviate it by p. So when I write p, I mean the random variable p of g. So p of g. And we get the following thing. So we want to estimate, if you recall, we want to estimate the 2pth moment of capital P. And how do we involve this guy here? If you recall P was 1 plus zg plus g squared. Well, we want to get something that's amenable to this cumulant expansion, and we will just rewrite this with that. Okay, we will rewrite this as the right-hand side, and then you see this is so we will take one of these factors of p, and we will leave all the others unchanged. So let me write it like this. So this is p times p to the p minus 1 times p bar to the p. Okay, this is a trivial change, and now I will not touch these guys for now. I will just rewrite this using that identity. So this is equal to the expectation of 1 plus zg gives me 1 over n ij hij gji plus I still have the g squared, and then I have my p to the p minus 1 and p bar to the p. So if I want, if I may, I will not write these parentheses anymore, right? The expectation is always understood to act on everything on the right-hand side. Anything that's a random variable on the right-hand side is inside the same expectation. Okay, so here we are, and now we see very clearly how to apply the cumulant expansion, you see. So this term, we'll leave it for now, the g squared. We'll deal with it later. The first term here, you see I just get a sum which I can pull out. I have an hij which multiplies gij and then this product of these p's. And this is just a big polynomial in the entries of g and its complex conjugate. So we can apply this formula and differentiate and see what comes out. Okay, so let's do that. So now we apply the resolvent expansion. Let me apply it to this term. We got this sum over k. So I get k goes from 0 to n. And then I have 1 over k factorial. And then I have this sum 1 over n ij ck plus 1 hij. And then I have the expectation of the kth derivative of this function. And what is the function that this hij multiplies? Well, it's gji p to the p minus 1 p bar to the p. Okay, so this is the crucial application of this lemma 27. I just take it from up there. H, now these variables are all independent, so I can pull out the sum. hij is the little h. And I get this. So my function f of h is this one. This is f of h, which is clearly a function of hij. Right? It's the green function. It's a product of entries of the green function. And then I get a few more terms. So of course I get the term g squared. So I get the expectation of g squared, p to the p minus 1, p to the p. And then finally I get the remainder term, 1 over n. And this, so let me give these guys a name. So this term, the remainder term. So this notation, I hope it's clear, right? I have a sum. If I pull out this sum here, 1 over n sum over ij, then I have a direct application of this formula. So for each ij, I apply this formula. And the remainder term here, that I denote by Rn plus 1 ij, is exactly this one that you get from the cumulant expansion for hij. So let me call this this guy R. Let me call this guy B. And let me call this whole thing AK. Okay, so this AK is the kth term of this cumulant expansion. So now we have to analyze these different terms. So in common with many arguments in analysis, the underlying ideas are very clear and quite beautiful, but if you want to make a rigorous proof out of them, you sometimes have to worry about some technicalities and write up lengthy expressions and so on. But I try to choose the simplest instance with a simplifying assumption so that the main argument remains relatively transparent. And of course here I introduced a parameter n to be chosen later. So this n, I can choose it as I wish. You will see, we will see later how one should choose it. Basically, it's going to be fixed. You just have to choose it large enough such that these remainder terms are very small in some relatively trivial way. And these are not difficult to estimate. The main difficulty is in analyzing these terms AK. Okay, so let's start. A0. What's A0? Any ideas? So it's if I ask it, it means the answer is relatively simple. If you look at A0, there it is. This guy is C1 of hij. What's C1 of hij? C1 was the first cumulant, which is equal to the first moment, which is equal to the expectation. right? And the expectation of Hij is 0. So this is 0. Okay, so that's the first one. That was easy. Let's see if the next one is as easy, and the answer is no. The next one requires some computation, but the next one is also the most interesting one. So everything happens in A1. So let me just recall what this was. So if I take k to be 1, then I get C2 of Hij, which was the variance of Hij. And if you recall, I chose it to be 1 plus delta ij over n. So A1 is equal to 1 over n. And then I have a sum ij. K factorial is 1. And ck, so C2 of Hij is 1 plus delta ij over n. And then I have the expectation. And then I have the derivative. I have the first derivative. K is equal to 1 of this. Okay, that's just the first derivative in Hij. So this is A1, and this is something we have to compute. So let's start by doing the computation of this derivative. That's what we have to do, right? So this is the key. Basically, this argument consists of just two things. You will get derivatives of this guy. You have to find some systematic way of computing these derivatives. And then you get some expressions for these derivatives, and then you have to figure out how to estimate their expectations. And both of these are in principle very straightforward things. So it does not require any fancy mathematics, any deep knowledge about anything. It does require some care in organizing these things right. So the difficulty in these arguments, and this is in common with many arguments in various areas, most notably in random matrix theory and more generally in mathematical physics. It's a very common problem in mathematical physics, is that you have some procedure that generates terms in a very elementary and obvious fashion, but as you go on, the complexity of these terms increases, and you have to find some way of keeping track of what these terms look like. And in particular, you may have heard about Feynman diagrams. This is why these things were introduced, in order to keep track of complicated algebraic terms. And depending on the complexity of these types of arguments, they can also be very well managed using Feynman diagram type methods. Here, this is much easier, so we will not need that. I would like to keep everything very explicit. So we have to calculate this derivative. So calculate 1 plus delta ij of the derivative gji e to the p minus 1. Okay, so the derivative by the product rule can hit this term, or that term. Okay, so let's write up all possibilities. So if it hits the first term, recall by the formula I had before, I get two terms. One is gjjgii, and the other one is gji gji. So let me write them up separately. So gjj gii, and then I have p to the p minus 1, p bar to the p. And the other one is gji gji. Okay. So these are the two terms. Recall the differentiation formula I had for this partial ij. These are the two terms I get if I differentiate this one. Okay. Now, and then I get two other terms, which is one where they're basically the same. But let's assume I differentiate that guy. If you recall, p was 1 plus zg plus g squared. So by the chain rule, I will get the partial derivative of this will be p prime will be equal to p prime times the derivative of g. And p prime is equal to z plus 2g. Okay, it's the partial derivative in the argument g. So if I do that, I get minus I have p minus 1 of these terms. Right, so I get a p minus 1. And then I will have gji, which I did not touch. And then I have the p prime. And then I have a sum. How do I differentiate k? This is p prime times 1 over n, sum over k. Okay, this is how I can differentiate little g. I write little g as the average of these gkks. And here again I apply my formula. And this time you will see you get let me do this. So I will write these little calculations on the side. I don't want to interrupt the flow of the main calculation. So this is equal to gki gjk, and then I get minus gk j gi k. Okay? So if I do all of this, I get the minus, I get p prime, I get sum over k, and I get gki gjk plus gkj gik, and then I still get what remains is p to the p minus 2 times p bar to the p. Is okay? So a somewhat lengthy expression, but there's not much really going on. And then there's finally the one I get if I differentiate this guy is exactly the same. Minus p gji, I have p prime bar 1 over n k So this is what I get. This is the full differentiation carried out. Is this all right? Just differentiate everything mechanically. Okay, now let's look at these terms a bit. So let me give them names. This one is A, this one is B, this one is C, and this one is D. So let's analyze them one by one. So what do we have to do? We have to take each of these terms and plug them into here, right? I computed this 1 plus delta ij times this derivative, and therefore I just take 1 over n squared sum of I and j, take the expectation of each one of these 4 terms individually. So if I do that, something very wonderful happens to the first term. So what will turn out to be the case is that B, C, and D are all very small, and A is not. Remember, what we are trying to show is that what we are computing, this whole thing is going to be tiny. It should be very small. A is not going to be small, but A is precisely going to cancel the term capital B that we had before. And that's very easy to see. So now so we take 1 over n squared sum over I j of the expectation of all of these terms of A up to B. So A what does A give? So we can do this immediately in our heads. If you take 1 over n squared, take the expectation 1 over n squared and sum over I and j of this guy. This gives you little g, and that gives you another little g, right? If you sum over I and j. So this gives exactly, but with the minus sign, expectation of g squared. I get 2 little g's from the averages over I and j, and p to the p minus 1, capital P to the p. Wow. And this term is exactly equal to minus b. It's an exact cancellation. And this gives you an exact cancellation with b. So this is a feature of this approach, is that you get such exact cancellations. And another way of seeing that is that the term little g squared, if you recall, the term capital B was, so B was, that had the expectation of g squared p p to the p minus 1 p to the p. This was the term that came from the quadratic term in my polynomial p, right? This was the term that came from that one. And another way of viewing it is that this calculation, if you did not know which quadratic polynomial to choose, this calculation would tell you which one you have to choose. You have to choose g squared because this term has to be cancelled by the quadratic term in this polynomial. And so if you want this simple differentiation that we did, that is another very straightforward way of seeing why the semicircle law has to appear in this business. Simply because you want this term to be cancelled. Therefore, your polynomial, so you start with a polynomial 1 plus zg. This came from this defining relation of your green function g. And then you see that for the expectation of the moment of this guy to be small, the next term has to be a plus g squared in order to cancel precisely this term minus g squared that you get by differentiating this. You have to have a plus g squared to cancel that. And this is the defining equation for the Stieltjes transform of the semicircle law. So if you wish, this differentiation that we just did is maybe the most straightforward or direct way of seeing another way of, well, a very direct way of seeing the semicircle law appear. Okay, is this all right? Is it clear to everyone? Okay, so this was just a computation, and all the others we have to estimate. So let's estimate them. So what does B give? So B gives minus the expectation. So I just take the expectation and I average over I and j. 1 over n squared I and j. And now I will show you there are basically 2 tricks one has to apply to show that these terms are small. One of them we've already seen and used a lot. and that's this Ward identity. So this is bounded in absolute value. Let me not try to be smart. I will just take the absolute value inside everything, inside the sum, inside the expectation. So I get the expectation 1 over n squared, sum over ij, gji squared. If I take the absolute value of these p's, I get p absolute value to the 2p minus 1. And now I can use the thing we always use to estimate these kinds of things, which is this Ward identity. This is lemma 17, which we call the Ward identity. And so if you recall, in fact, by the Ward identity, this thing is equal to that. Right? If you recall the Ward identity, you can sum over I first, for example, and then you can sum over j, and you get precisely that. So we get the imaginary part of g times, so all this inside the expectation, of course, expectation times p to 2p minus 1. Okay, and this is as far as we can go with this term. We will see at the end how everything comes together. But what we have, if we manage to prove, and we will, that the whole right-hand side, so what we are estimating, I remind you, we are estimating the following thing. If we manage to prove that this thing is bounded by terms of this type here, we will be in very good shape. It's going to be an easy application of Hölder's and Young's inequality. We'll do it later today. So our goal, you see, why morally, why does this look good? We've reduced the power of this p by 1. So instead of having p to the 2p, I have p to the 2p minus 1, and I replaced one of the factors of p by something that is small, right? This I know to be small. I know that this guy is bounded. I know that n eta is very big. So this is a very small factor. And then I can just apply Hölder's inequality to LP norms, and I will be able to conclude that, in fact, such a guy has to be bounded by the LP norm of this guy here. We'll do that after the break. We should indeed have a break, so let's have a break now, and we resume at 20 past. Okay, so let's continue with these estimates. So we dealt with A and B, and we would like to now deal with C and D. They are basically the same. So let me start with C. So what do we get? C gives the following. So I have a minus p minus 1, and then I have a sum. So I had the sum 1 over n squared over sum over I and j, and now I have another a 1 over n, and I sum over k, so I get a 1 over n to the 3 sum over I, j, and k. And now you see, if I swap I and j here, I can rename the summation indices in this term, and I get exactly the same one as that one. So I can put them together. I get minus 2, 1 over n to the 3 I, j, k. And then I have the expectation. Actually, maybe if I may, I will write it. I will write the order a bit differently. I will start. I need a longer line. So minus 2, p minus 1, and then I have the expectation. ijk, I took out the p prime, and so I have gji. Let me reorder these terms. So let me write it. So I have G, it doesn't really matter, I just have GJI, and then I have G, well, I will use the fact that my matrix, if you recall, is symmetric. So H is equal to HJI, because I assume the entries are real, which means in particular, so this matrix is symmetric. It's not Hermitian, but it's symmetric. Right? This is Hermitian as well. This is real Hermitian. This is not Hermitian, but it's symmetric. So I can write it as G. I can swap these indices as I wish. So I will have Gij, which comes from this one, Gji. Write it as Gij, and then I have Gjk, and then I have Gki. Okay, from this one. So I swap the indices. I have Gij, Gjk, Gki, and then I have p to the p minus 2, p bar to the p. Okay. So now comes the second thing we have to use in order to estimate these terms is how to figure out these kinds of sums. So in the previous term, when we dealt with b, we had a sum over two summation indices. We could just take absolute value and use the Ward identity. In this case, it doesn't quite work. You have three terms and you have to be a bit more careful. If you take in absolute values, I mean, you can try to involve the Ward identity in here somehow. And of course, for example, if you fix I and j, you can sum over k using the Ward identity and some Cauchy-Schwarz. This will work. But then you are stuck with the I and j, and you are not exploiting the summations in a strong enough way to get what we want. So here the observation that one has to make is a very simple one, is that this is just 1 over n to the 3 times the trace of g to the 3. Okay, that's just by definition. And in fact, let me estimate it like that. So the absolute value of this is equal to the absolute value of the trace of g to the 3 divided by n to the 3. I can now rewrite the trace in the spectral decomposition. So it would be the absolute value of this guy. I can get an upper bound if I take the absolute values inside. Okay. Now, what I would really like to arrive at is something analogous to what we had before. I would like to arrive at something like the imaginary part of g over n eta or something of that kind. That was our goal. And how am I going to do that? So let me, in order to figure out what we have to do to this guy, let me recall what was the imaginary part of g. Imaginary part of g, so it's the imaginary part. This is a calculation we've done many times before. Okay, so this is the imaginary part of g, right? So let me try to smuggle this in somehow. So I'm still just calculating this small piece, so this is kind of a little calculation on the side. So let me sort of forcefully put the imaginary part of G in this business, so I have 1 over n. Okay, now that's of course not an equality. I still need to do a variety of things. So first of all, that is still not quite okay. That would be okay. So this is an identity. This is just a very complicated way of writing the same thing, but I wrote it like this because I wanted to extract the imaginary part of G, right? That's the imaginary part of G, and I think I need a squared here. Okay, now it's correct. So the etas cancel, right? This gives me a lambda I minus z to the 3, and I have 1 over n to the 3, so it's all okay. And this, I will just estimate it by 1. Right? This is the imaginary part of that number, so this is clearly bounded by 1. So the conclusion, and this is what I wanted to get, is that this thing is bounded by n squared, eta squared times the imaginary part of G. So this was the second key idea in these estimates. You write it like this. You go from the indices to the eigenvalues. That's a highly non-trivial transformation. And then you can take in absolute values. And sometimes taking in absolute values on the level of the entries is good. And it's not at all equivalent to taking absolute values on the level of the eigenvalues. And in this case, this yields a better bound. And this is going to be good enough. Okay. So therefore, now I can conclude. I'll be done. So the expectation, so 1 over n squared, sum over I, j, expectation of C is going to be bounded by, now I have this constant 2 times p minus 1 and so on. I don't really care about these constants. If one wanted, one could track them, but I'm not interested in them. So let me write it like this, big O of 1, and I keep a subscript here to remind myself that this is a constant that depends on p. Okay? So this notation is just my notation for a constant that depends on p, which in this case is just 2 times p minus 1. In fact. But I will have other terms of this kind, and I'm not interested in tracking these constants in p. Okay, so then I get the expectation of the imaginary part of G. Then I had the polynomial, the derivative of p, so absolute value of p prime divided by n eta squared, and that's it. And then I just have times p to the 2p minus 2. And this is again, this is the end of this calculation. So you see, we obtain a very similar kind of bound. So all of this will go into the estimate. I remind you, into the estimate of this. Okay, so we were able to estimate this in terms of a term of this kind. So it's, instead of having a power 2p, we have a power 2p minus 2. So we lost 2 factors of this polynomial p. However, we gained this guy, which is small. And if you see, we gained 2 powers of n eta. We lost 2 powers of p. We gained 2 powers of n eta. And that is, in fact, a general kind of balance in this argument that will become, its importance will become apparent in a few minutes when we do the Hölder estimate. Okay. So let me now do D. D is basically, it's exactly the same as C. So let me just sketch. You see, I'll show it to you on the board. I will write up a few details, but you see, you could basically do it yourself. The only difference between C and D is that you have a few bars here. right? I have two complex conjugates on these g's. Otherwise, it's exactly the same. And so you may worry about complex conjugates. In general, they can be truly dangerous because G, if you multiply entries of G, usually they are much better behaved if none of them have complex conjugates. If you start putting in complex conjugates, in general, the resulting quantities can be much bigger. In this case, that's not going to happen. And the argument is exactly the same. So let me just explain the difference. So D to C using that, so I just erased D very cleverly, but if you recall what it was, you have the same expression. Gij, gjk, and gki. And this is what I have to estimate. So it's the same thing as here, except I have two complex conjugates. And now the observation that you make, I have into the 3, is that this is equal to so you can still express it as a trace of the product of three matrices. It's not G times G times G, it's G times G bar times G bar. And this you can write in the spectral decomposition exactly in the same way. Okay, so you get exactly the same thing, except the two of these guys, two of the z's carry a complex conjugate, and this is now estimating exactly as before. So I get the same bound here, and then I can repeat exactly what I did. And I get the same. I get this exactly the same bound as here. So let me summarize, since we've worked quite hard. So the conclusion is that A0 plus A1 plus B, there was this crucial cancellation, so I take in the B as well. This is bounded by some constant times the expectation so this was the term I got from the term little b from A1, if you remember. And then I get this term that I got from little c and little d. That's the conclusion. So here you see again this structure very nicely, that you will get, in fact in general you will get more terms. I will explain that a bit later, but this really shows you what's going on in this argument. Is you replace, if you recall, this whole thing were the main terms in the estimate of this guy, the expectation of absolute value of p to the 2p. And you get the expectation of the same kinds of moments, except you reduce the exponent of p. If you reduce it by 1, you get the first power of such a guy. If you reduce it by 2, you get the second power. Well, it's not quite this guy. One of the imaginary parts of g has been replaced by p prime. but if you count the denominators, you get a second power of this. And that's a coherent structure that is important for the conclusion of this whole argument, which I would like to explain now. Now, I remind you that we just did A1, okay, and then we should do A2 and A3 and A4 and A5, okay. So you saw A1 already took some work, so you might imagine, my goodness, well, what are we going to do with A2 and A3 and A4? In reality, they are actually less delicate to analyze. So the higher order terms are in fact easier for two reasons. The first reason is that we get these cumulants. If you recall, ck plus 1 of hij, this is of order n to the minus k plus 1 over 2. So as you increase the order, this was the homogeneity property of the cumulants. If you increase the order k, then you start getting extra factors of 1 over square root of n. So these things start becoming very small quite rapidly. And the other observation is that the more you differentiate, the more such polynomials, or the higher the degree of these kinds of polynomials in G is going to be, the more summation indices you have, and the more you will be able to apply Ward's identity. And therefore, the more factors of this kind you will get. This is the basic intuition. In order to do implement this precisely requires some thought about how to organize the algebra. I would not like to do this now. Instead, I would like to show how to conclude the argument just from these two terms. And I can in fact do that in a clean way if I assume that my matrix H was a Gaussian matrix. So that's what I would like to assume now. And then you know from this problem set that we did for today that these terms are the only ones. A0, A1, and B are the only terms. If your entries Hij are Gaussian random variables, then the higher order cumulants all vanish. So if k is 2 or more, you get a third or fourth or fifth cumulant. This is 0. And the remainder term is also 0. And therefore, if the entries of H were Gaussian, this is it. There's nothing else. So that A2 is equal to A3 is equal to R is equal to 0. So I will return later to the general case. The moral is that the general case doesn't really change. It's basically the same. You get these additional terms, but you just have, it's a bit more technical. I will explain in words. I will not do the full details because it's not so interesting to see, but I hope to show you that it's kind of clear that it works. If you include these higher order terms as well, they become very small. And the same argument works for any Wigner matrix. So, I in fact already gave you the key ideas why the general case works in the same way. These two features, I will explain them in more detail after we complete this proof for GOE. Okay. So, I would like to, let's figure out, we have to understand a bit better this polynomial P prime. So that's a very simple fact. So what is this P prime? So it was P prime at G, which, if you recall, P prime is nothing but Z plus 2G. And I would like to estimate, I would like to replace the g with an m. So I can do that. 2m plus 2 theta. Right? Theta was the difference between g and m. And z plus 2m, if you recall this, now you can just plug in the explicit equation for m, which you get by solving this quadratic equation. And z plus 2 times m is precisely equal to, this was by lemma 8, this is equal to right, if you recall, m was equal to minus z plus the square root, the whole thing divided by 2. If you multiply by 2, add z, this z cancels, and all that remains is this. And this guy here is precisely in fact, this is of order, so this is asymptotically the same as kappa plus eta. This is just the square root of the distance of z to one of the roots, 2 plus 2 or minus 2. And that is exactly this thing here. Right. Is this clear? This is just, I mean, you can write this as minus 2 and because z is bounded, we are always in this domain, in the spectral domain, in the rectangle with bounded absolute value for z. This guy is going to behave like the shortest, the smallest one of these two, the square root of the smallest one of these two numbers, which is precisely the distance of the real part of z to 2 plus the imaginary part. Okay, so it's this one. And moreover, I will need I remind you that the imaginary part of m we figured out the precise behavior of the imaginary part of this thing. This was always bounded by kappa plus eta. So now one of the things we are aiming at here is a precise description of what happens near the edge. And there's something interesting happening there. And then these kinds of, the behavior of the imaginary part of m relative to these kinds of expressions become very important. If you recall, in lemma 15, we said that the imaginary part of m, it was in fact of the order kappa plus eta if e was less than or equal to 2. So then this is sharp up to a constant. This is sharp. And if you are outside of the spectrum, it's not sharp, but it's definitely an upper bound. So this number, so this is the same one, of course, and this one is clearly bounded from above by that one. Okay. So these are some preliminary observations. So let me now define, looking at the conclusion, let me keep the conclusion here. I would like to just introduce some notation so that this conclusion looks a bit more palatable. So I will define a variable, a random variable x, in such a way that this guy is bounded by x, and this guy here is bounded by x squared. So basically, in an ideal world, x would be in fact this would be imaginary part of g over n eta, which I would estimate. I like to write things in terms of m and not g, which means I have to pay the price of these factors theta. So in an ideal world, I would like to have it in terms of this parameter. Okay, so then this is clearly, if I defined my x to be this guy here, this were my x, then this would certainly be true. Unfortunately, this would not be true because it's a product of two terms. The first one is clearly my x. The second one is p prime over n eta, and p prime we saw is bounded by this, and the inequality goes the other way, right? This thing is not bounded by imaginary part of m. Imaginary part of m is bounded by that guy. Okay, so unfortunately it goes the wrong way around, and this in fact is important when we are outside, and this will be important when we want to understand, for example, the largest eigenvalue or the spectral radius of this matrix. Then these two quantities can be very different. So, of course, what one could do is to define the x to be quite drastic and to define the x as taking this guy squared, because we know the bound we have here is going to be a bound for imaginary part of g as well. So we could choose our x to be kappa plus eta. Then these would both be correct, right? This imaginary part of g is bounded by that. It's bounded by this, and that's bounded by that. But that's a bit too drastic. And in fact, for some arguments we want to do later on, this is too much. So what I will do is I will take the geometric mean between that and that. And this is true. This works. So defining x to be, so I take the imaginary part of m plus theta times kappa plus eta plus theta so it looks a bit unwieldy, but actually it's not too bad. We conclude that. Now we can finally summarize everything. Let me write this in the LP norm notation. It's exactly the same. So this number here is exactly what I wrote here. So this is equal to some constant that depends on p, and I'm not interested in. And then I have these two terms, and I will write them together. Q goes from 1 to 2. The expectation of x to the q, p to the 2p minus q. So this is the conclusion of all of our estimates. And I don't need this bar here. Okay, is this all right? So again, if I had chosen, so this is the term q is equal to 1, and this is the term q is equal to 2. Okay, so if I had chosen my x to be this guy here, then the q is equal to 1 term would have worked. But if I want both to work, I have to choose my x to be slightly larger, and I have to replace, I write this as a square root of this guy squared, and one of these two factors I have to replace by square root of kappa plus 8. If I square this guy, I get something that is clearly an upper bound of that. Okay. All right. So now this is now an elementary problem using LP norms. So from this we want to deduce that that this guy is in fact bounded in terms of x, bounded by some LP norm of x. And this is just an exercise using Hölder's inequality, so let's do that carefully. So let's apply Hölder's inequality. Let's apply Hölder's inequality. Apply Hölder's inequality to this thing here. Now you see the sum of the exponents amounts to 2p, right? So we will be able to get using Hölder's inequality, we will be able to express this as a product of two factors involving the 2p norm of that guy and the 2p norm of capital P. And in fact, you can work it out just by homogeneity. I mean, of course, you can calculate these Hölder exponents exactly, but you know that this guy has to be homogeneous of degree q in x, and therefore that's the right exponent. And the same thing for p of g, 2p, and this has to be 2p minus q. Okay, so you see this is kind of it's a closed inequality for this quantity, for the 2p norm of P, of capital P, and there are various ways of doing this. Maybe the most transparent one is to use Young's inequality. Let me introduce a parameter epsilon, which is convenient to take to the power. I mean, there are many ways of doing this. Everyone has their own favorite way. I will give you one. I write 1 here. Okay, this is a trivial way of writing 1. And then I use Young's inequality, which, if you recall, says that a times b is less than or equal to a to the p over p plus b to the q. I should not use p. A to the r over r, b to the r prime over r prime, where 1 over r plus 1 over r prime is equal to 1. That's Young. For some reason, many people call this the Schwarz inequality. People have somehow this reflex of calling absolutely everything where you do some kind of inequality to decouple a product Schwarz, but it's not really Cauchy-Schwarz. It's Young's inequality. So if you apply Young's inequality, and again the exponents to choose are clear. I choose the exponents in such a way that I make this guy equal to 2p. So I want to exponentiate this guy, which would be, let's say, the r. I would choose my r to be equal to 2p over 2p minus p. Okay, and then everything else is defined. And if you do this carefully, I get a factor epsilon.
R is
2p minus q, yes, thank you. 2p minus q. So that's this guy, and then I get the other guy. I split this into a sum. And if I did my computations right, you get the following thing. Okay, so this sum now, of course, doesn't do anything. We can just replace it with a factor 2. Doesn't really do much. And now I want to be able to close this equation, right? So this was an estimate for this quantity, and I can close it provided the prefactor here is less than, let's say, 1/2. Okay, then I can bring this to the other side. So if I choose my epsilon to be equal to 1 over, so if I take this I call this guy big OP of 1, I keep the same terminology. So I have 1 over 4, big OP of 1. So this is going to cancel this 2, and it's going to cancel that, and still a factor 1/2 is going to remain. I can bring it to the other side. Yields finally 2p. Well, I can keep the exponents. So that's the conclusion. So this is the conclusion of all of these estimates, and that's what we were aiming for. So we've managed to estimate the L2p norm, so a high norm of this polynomial p, in terms of the corresponding high LP norm of this error parameter, which is still random, but it's very explicit and it's manifestly small. And then by using Chebyshev, it's going to be easy to conclude. Now, it's not that, so I think now you see this, it's kind of clear what to do. There is one issue which one has to worry about. So what does Chebyshev, so we will do that, we will finish this next time. I just want to explain what you have to worry about. So Chebyshev tells you if you have a random variable, so in particular the version of Chebyshev we are using, say Chebyshev for moments, if you have a random variable x, which is, well, a random variable, it says the probability that x is bigger than or equal to t. This is bounded by okay, so this is Chebyshev, right? And this is Chebyshev for moments. Except this t has to be a deterministic number, and this guy here is not deterministic, and so what we would really like, well, we would really like to replace this x with a deterministic bound that we can use as t here. That's in fact not a major problem. There are various ways around that. So the easiest way is to take some deterministic function, assume that theta is bounded by this deterministic function, do Chebyshev, and then verify this assumption. And that's what we'll do next time. I think, yes, now our time is up, so let's stop here. This was the conclusion of this main estimate. Next time I'll show how to use this and Chebyshev to conclude the whole argument. We'll discuss a bit also how to do this for general Wigner matrices, this extension to estimate A2, A3, and so on. But otherwise, this was really the core of this argument. And this is a very powerful and important argument that we saw today. It's applicable and has been applied to many, many different contexts and many problems, and it's very versatile. Okay, so we'll conclude this whole section next time.